Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
Do you feel like our friendship would benefit from some distance?
Oh no, why would you say that?
Well, you know, me and my jokes, it can be a lot sometimes. Do you maybe need some space?
I assume there's some sort of pun intended here, which neither me nor our listeners will get, but actually you raise a good point. Maybe I'll consider that offer.
So you don't think we resonate?
In fact, I doubt it.
That we not only are on the same page, but on the same frequency. Well, good news for you. Today we'll be digging into the topic of radio waves and space and satellite communication with a researcher and engineer who works here, in Graz.
Her name is Mirela Fetescu and she happens to be a good friend of ours.
But before we start with our guest, I just wanted to give you reassurance about our friendship. As we will see during the episode, even if we end up on two different satellites, I would still be able to contact you. We could still wave at one another.
The probability of this scenario is exactly equal to my excitement about it.
So, very low?
You're smarter than I expected today.
But anyways, as usual, we asked the students what they knew about the topic, and that's what they had to say.
I don't know who Guglielmo Marconi was, but I know that radio waves are part of the electromagnetic spectrum with wavelengths much longer than light. So they have much lower energy, and I suppose, as the name says, they can be used to listen to the radio. And I know that they can be reflected on the stratosphere, so they are very useful in sending information all around the globe.
So, Mirela, can you please introduce yourself, tell us about your skills, expertise, your background? Stage is yours.
Yeah, thank you, Tomas, and thank you, Daniel, for inviting. It's a pleasure to be here today. Well, I am Mirela Fetescu, and I am a satellite communication engineer at Joanneum Research in Graz. I was always fascinated on how information travels, and when I discovered that we can reach very distant places in such a short amount of time, and telecommunication allows to shrink distances, I said, okay, this is what I need to do. And that's where my love grew for satellite communication and space.
It is my understanding that in telecommunication, electromagnetic waves play an important role, right?
Absolutely.
So, can you give us an intuitive intuition of what an electromagnetic wave is?
Yeah, of course, electromagnetic wave is the basic, I would say, for wireless communication. And not only wireless, actually, I guess, in every media. And an electromagnetic wave, it's a type of wave that propagates through space and time, carrying energy without the need of a medium. It can propagate in air, also vacuum, or even other materials, but not necessarily. And these waves are made up of oscillating electric and magnetic fields that are perpendicular to each other and perpendicular to the direction of wave propagation. So electromagnetic waves travel at the speed of light in vacuum. Now, why the electromagnetic field is called like that and why electric and magnetic field oscillate? This is due to the fundamental nature of electromagnetism described by Maxwell's equations. And the equations govern how electric and magnetic fields interact with each other and with charged particles. So, according to Maxwell's equations, charging electric field generates a magnetic field, and the changing magnetic field generates an electric field. So this is known as the mutual generation between electric and magnetic fields. And the time-varying electric field creates a magnetic field and in turn induces a change in electric field. So this back-and-forth interaction results in self-propagation of electromagnetic wave through space. And this is why. So we can we use this to carry our signal, to carry our information.
So you talked about electromagnetic waves, and now you mentioned radio waves. Is there a difference between the two?
Well, the electromagnetic waves is the more general name of electromagnetic wave, so to say. It can happen at any frequency. Radio wave is it's some part of the spectrum, so a certain range of frequency. And in the SATCOM community, we usually talk about radio waves or some optical. So even the optical visible are some electromagnetic waves in the terahertz frequency, while the radio is usually used to say from kilohertz to some gigahertz. And nowadays in satellite communication, we used to call a radio then in the gigahertz range, where now all the SATCOM happens.
So now that you brought up satellites, when I hear satellite, the first thing I think of is like GPS, television, or Starlink. Yeah? Are there any other applications?
There are actually a lot of applications. Well, telecommunication and satellite communication, this is one of the very known. For video broadcasting, we have satellite TV with international broadcasting. Then we have satellite phone calls. This is an emergency backup for our terrestrial communication networks. Internet via satellite, like as you mentioned, Starlink. Also in-flight and maritime connectivity, so we can have internet on our cruises or when you're in flight. And also for in cases of emergency and disaster, when something like floods or earthquake can happen, then or an attack or war, terrorism, anything, where the ground infrastructure lacks in that moment, then satellites can be the first responder communications. Navigation as well, as GPS, as you mentioned, this is more known as GNSS, Global Navigation Satellite Systems. And it's not only GPS, this is American, there is Galileo in Europe, GLONASS, which is Russian, and some others that exist. And this is indeed for navigation. Moreover, Earth observation satellites, they're usually in low Earth orbit, and they're used to monitor Earth's surface and atmosphere, for environmental monitoring, weather and climate, disaster response, to monitor agriculture, and for urban planning. Then we also have something like science and deep space, where our satellites either are in Earth orbit still and look at the Earth for Earth science, or outside for space science towards the universe, or they leave the Earth orbit. So we name them this deep space because they're going and leaving Earth orbit.
How does a satellite get its energy, sort of? Or what's the energy source for the satellite to work, sort of?
Sure, nothing happens without power. And in our communication links, of course, we need power, but not all in the telecommunication subsystem and all the subsystem of a spacecraft. And usually the satellites have solar panels. Some might have some propulsion in it, with some fuel for some maneuvers in orbit, but most of the operations and then mission and during the live mission, then it happens with solar panels. So these are specifically designed, depending on the orbit, to catch as much sun as possible to transform this in power.
So since before you mentioned atmosphere, I have to ask this. How does atmosphere influence the communications? And can you tell us a bit about maybe how the field started? For example, like when did we really started to have this transmission from place to place with radio waves? So can you tell us about a bit of the history also?
Yes, definitely the atmosphere influences the electromagnetic wave propagation. And, well, as I mentioned earlier, we have a spectrum and we have different frequencies. This means we have different wavelengths. And there is an example I really like to tell people not from the field or maybe not from science at all. Is imagine you have a laser that you shoot at a wall. And, of course, laser is in terahertz, right? And you shoot at a wall that is some centimeters thick. Will you see anything behind it at all? No. Well, okay, now we have Wi-Fi in our houses, 2.4 gigahertz. Wavelength is much bigger than the one of the laser. It goes through walls, so we have transmission. So this is more or less the principle, what I'm talking about. So the shorter the wavelength, the more impact we will see from the molecules present in the atmosphere. So it's the same effect. When we have a low frequency, then only some components will have an impact. For example, maybe rain, or maybe not even that. If we have a higher frequency, then of course, even the gases present in the atmosphere, rain will be a big impact, clouds, and so on. And talking about it, there are some gases, in particular water vapor and oxygen impact, especially in some resonating frequencies. So they're known as absorption peaks. So that's usually where we should avoid to make our transmission bands. And these are known. The clouds, This is again depends on the thickness, on the density of the clouds. The rain is a big contributor. We have different rain shapes, sizes, and some absorption phenomena can happen. So the energy from the wave is absorbed by the water drop, but also scattering. This is to the higher frequencies. So all the incident electromagnetic wave scatters in different directions. And then all this energy is dissipated not in other directions, so it does not reach the receiver. But also depolarization. So a wave has also polarization. This is the direction of the electric field. And we can use linear, circular, or other. And usually our receiver is in sync with this, so is already set for one certain polarization. And when the wave would go through the rain and different raindrops, this might result in a different direction of the electric field at the end overall. So, of course, if there is a wave transmitted with certain polarization through all these raindrops, then at the end, the resulting electric field direction will be different, and this will result in a loss of power at the receiver, which is already set to listen to a certain polarization.
You mentioned so many issues that there are when trying to do satellite communication. I'm somehow surprised it works at all. So there have to be a lot of very clever tools and tricks to circumvent this, no?
Of course, first of all is to carefully select the frequency bands. Well, we have frequency management from the International Telecommunication Union, so we cannot just choose the frequency we like because some bands will be allocated or pre-allocated for certain services. So then we first to be aware which is the service we want to use. Then also the frequency that is more suitable. So if we know that there is an absorption peak somewhere in the band, we will avoid that one. Rain we cannot really avoid, this is for sure. And we have several fade mitigation techniques. So it will not rain all the time, first of all. And when it rains, we can do one example is adaptive coding and modulation. So for example, we will have a more performant modulation. We can send more bits per second when it's clear sky. And then when the signal starts to drop because it loses power, so the signal to noise ratio, this is a key performance indicator, in our field will be lower than a certain threshold, then we move to a different modulation that requires lower signal to noise ratio to function. We'll transmit less bits per second, but our link will be maintained. This is one thing. So not only changing frequency, once you choose your service and your frequency, that is the frequency band, but also we can play later on with some signal processing, so to say. So some fade mitigation techniques as adaptive coding and modulation. This is very well known and very much used.
What is fade mitigation technique?
Every time there is a change in the signal, and especially when it drops, there is some fades. So there are some slopes that happen drastically sometimes. So we try to mitigate this.
Is this done automatically, or there's an operator in there, like, turning the knob or?
No, of course, these are automated mechanisms and they operate automatically, yeah.
So you mentioned lots of satellites, lots of services, different bands where they work at. What are the challenges of having all these satellites in orbit, or especially for the commercial ones, for the internet ones in low orbit especially?
Mm-hmm. Well, first of all, there's a problem of space and space. So let's call it like that. We cannot keep putting satellites out there forever. They will end the mission life and they'll be useless. So we keep accumulating garbage. And then first thing that pops in my mind is space debris. So the challenge is to have all these pieces of satellites that are dead already. And we put even more mega constellations nowadays, especially in low Earth orbit, if we think about the internet mega constellations and all the commercial ones. And the distances are lower and lower. All these satellites go at extreme high speed. Orbiting around Earth, and the chance that some dead satellite can also break in some pieces is high. So even like a small piece of debris can cause a severe damage to all the other neighboring ones.
Sorry for the interruption, what are the speeds we're talking about here, if you have some reference numbers?
Approximately in low Earth orbit, a small piece of debris can travel to at a speed of 28,000 kilometers per hour.
That's huge.
So, I mean, as you say, there are a lot of satellites out there, a lot of debris out there already. First of all, is this being tracked? So does one know the trajectories? And second, if it is tracked, can you do anything to prevent the collision?
Of course, there are satellite operators, so this goes a bit out of my expertise, but there are operators that track specifically this. There are some initiatives also to clean space. So, for example, Clean Space, the European Space Agency, they also develop, as far as I know, techniques to how to deorbit these species or how to collect them and to bring them in the atmosphere, because then they burn and that's it. However, more modern missions, so to say, they really have to have a deorbiting plan. So when the end of life of mission of the satellite is reached, then they have to have a little bit of power to be able to make it back to the terrestrial atmosphere to enter, and they will be then destroyed. Of course, not only space debris, but we have to make sure that the existing satellites in operation, they are not colliding. And some frequency interference, of course, might be a problem because more and more services are there, and we have to share some bands or DSN bands. And there are more complexity and costs to monitor all these mega constellations versus a couple of satellites, for example, and to keep track of their health and status and to operate them overall. And also handover. This is also in terrestrial communication. It happens to handover from mobile phone to base station, from to base station. This is, of course, happens because then you have multiple ground stations on Earth. Low Earth orbit satellites are not constantly in the field of view of a certain location on Earth. And you have to make sure of inter-satellite handover to exchange information from satellites that are ending their mission life and the ones that succeed later are successors, and also handover between one satellite to another or ground station to another.
So when did the field of satellite communication take off?
Well, I would say that the beginning of the space age was with the launch of Sputnik 1 in 1957 as part of the Soviet space program. And it was the first artificial Earth satellite. So basically, the space race in the Cold War between US and Soviet Union made this takeoff happen. And each side wanted to prove their system superiority and winning the space race. So this was seen as an important means of demonstrating technological and scientific power. And space exploration became an important battleground for showcasing technological progress, and also intellectual capability and national strength. So we all know what happened later after this, but that was how it took off with Sputnik. Later on, Intelsat 1, also known as Early Bird, was first commercial communications satellite in geostationary orbit. It was designed to provide transatlantic telephone and television services, and it was the first scheduled transoceanic TV series. Then Mexico 70, that was a telecom satellite of the 1970, designed to provide satellite TV broadcast and telecommunications for Latin America. One key uses of Mexico 70 was to broadcast international sports events, such as the 70s FIFA World Cup, held in Mexico. And the satellite helped broadcast these major events to countries across Latin America and other parts of the world, making them accessible to a much larger audience. Mexico 70 satellite played a role in transmitting the event to global audiences. So this is a bit what happened with the first satellites, so space race on one side and TV broadcast on the other. And from there, we always got more and more and more in space.
Can you tell us about the history of radio wave communications?
Of course. Well, electromagnetism was something that scientists were investigating, studying, making experiments. But I think there was a key point in history where this had a major impact. And this was when Guglielmo Marconi, an Italian engineer and then entrepreneur, started to play with radio wave transmission radio because it was in some low frequency. And he was attempting to transmit electromagnetic wave and short range from one point to another, maybe from his door at the end of the garden. And then he tried more distance and more distance until he was bold enough to attempt a transmission over the Atlantic. And to me, this is a point where the whole perspective of radio communication changed it altogether. And that is the main important point in history where it was understood that this has a huge potential and now is the basis of everything we have around. Mobile phone, satellite communication, etc.
There is a very peculiar episode about this transoceanic transmission. Can you tell us about it?
Yes, back then, 1901, when Guglielmo Marconi wanted to send a signal from UK to Canada, it was not yet known what the ionosphere is. And many people...
And what is it?
Yes, the ionosphere, nowadays we know, it's the upper part of the terrestrial atmosphere. It's an ionized media, so it's sensitive to solar radiation, and it has some reflective properties at certain frequencies. It means that if you send specific radio frequencies, or in general electromagnetic wave at certain frequencies, it can reflect back or not, or it can go through. So nowadays we also can exploit, and that was what happened with Marconi, we can exploit these reflective properties to create links on Earth that are not in line of sight, which means two ground stations or transmitter and receiver cannot see each other. There is something in between, and we can still create this link with the aid of the ionosphere reflecting.
So you said it can be reflective or not. So I guess it depends on the frequency, but what else does it depend on?
Of course, it depends on the incident angle of the electromagnetic wave that we send, as well as on the frequencies. It's interesting that based on the season, time of the day, if it's day or night, the latitude, several layers, because the ionosphere is composed of several layers. Now we know it's D layer, E, F layer. They are different heights, but this can vary depending on solar radiation. So if it's day or night, this will be different. If it's different seasons, will be again different. And if it's different period of the solar cycle, which is 11 years, it will again be different. Plus the incidence of the electromagnetic wave.
So then I think it's very important to know the current state, right? How do you know that?
Yeah, it's definitely you need to know where these layers happen. Nowadays we have ionosomes that send pulses up at different frequencies, and then we can reconstruct the status or where the reflective layers of the ionosphere are. And then we can assess, of course, the height based on the delay of the signal when we receive it back. And then we can, of course, design our link.
This is really fascinating. Now I would move towards something specifically concerning your work. So what are your tasks as a telecom engineer?
Oh, my work can be quite diverse. I work in non-academic research, and we do research and some development. So some days can be really programming, developing simulators, or just code for our own purpose calculations, automating calculations. I'm involved in different projects. Specifically in my team at Joanneum Research in the digital department, we conduct propagation and communication experiments in QV band, which is 40 to 50 gigahertz, and as well as a W band around 70 gigahertz. And we have been the world's first in this. We have other interesting projects. I have been involved as well in signal processing and developing a pure software receiver with a digital video broadcast standard to receive satellite signals without modem, which is hardware, but purely software. As well as some research on the fade mitigation techniques that I talked already before, mainly due to atmospheric impairments in the signal, as well as ionospheric propagation.
In some of your recent papers, you applied machine learning to satellite communication, I think also in the context of signal-noise ratio. Could you tell us a bit about that?
Yes, recently I also started investigating machine learning, deep learning, and AI techniques in general to our world. So how could we use these new tools to our classical methods, and if they are better or not? So recently I started to study, of course, how can we make our fade mitigation techniques even more efficient and with less complexity, as well as how, for example, we can make an interpretation of ionospheric status, ionograms, completely automatic by means of deep learning.
And how well does it work? How much improvement do you get from machine learning, or is there improvement?
Well, of course, it's very challenging because AI in general works very well in some applications, for example, computer vision, large language models. And we try to apply some of this to completely different data that has completely different statistics. And as you may know, all this AI and machine learning heavily rely on statistics in the end of the day. And it's quite challenging to apply this to our data, which has somewhat complex statistics sometimes. However, there are some improvements, so it would be interesting to see them active in operation real time.
So one question that I have is, considering your work, what is the aspect you enjoy the most?
The aspect I enjoy the most is the fact that I'm working flexible hours. Aside of that, I really enjoy the fact that you can never get bored. I really like the engineering part because it's always new. You always have to adapt to new challenges, and specifically investigating new things in research. This is truly fascinating. You always have to be there on the most new novelties in the field and get to work with very amazing people.
Since you say working with amazing people, I guess also networking is an important aspect.
Oh, definitely. But this is not only in my field. I guess this is in every field. The more exchange you have, the more you know, and knowledge is power. And you can get inspired. And in the end of the day, you can never do anything alone. You would need collaborators. You need a team to make things work. And it's not feasible to just work alone.
So I guess that is why it's also important to present work on conferences and reach out, sort of, right?
Yes, that's a good point. And I am just right back from European Conference on Antennas and Propagation. It was an awesome event, and I had the pleasure and the honor to catch up with the old colleagues and get to know new people in the scientific community. Definitely. And you always come back more motivated with more ideas. And also you get to know what others think of your work. You also get very valuable feedback, and you can give, of course, feedback as well. So this is definitely one important part.
Well, we thank you very much for your enthusiasm, and thanks for being here again. And thank you all. See you next time.
Thank you.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.